So, Andres, if you wouldn't mind, if you can introduce yourself, I'll go through. That was Mary's slide to introduce us, and that's the BGS slide. If you just explain who you are and then tell me when you want me to change slides.
Hello, yes. Can you hear me?
Yes.
Right. So good afternoon, everybody. I'm Andres González Quiroz. I'm a geothermal scientist in the geothermal team, British Geological Survey. And I am standing in today for Corina Vesser, who's the Director of Policy, British Geological Survey. So next slide, please. So the idea of this presentation is to show some definitions and some of the potential of geothermal energy, and also to show the preliminary results of some prioritization maps we have done for some of the hospitals in England. So some of the definitions at start. So geothermal energy is the energy stored in the form of heat beneath the surface of the solid earth. So if we go deeper, it is getting warmer. So approximately there is around 30 degrees Celsius per kilometer depth when we go here in the UK. This heat mainly arises from the decay of natural radioactive elements, and also there is some part of the primordial heat from when the Earth was formed. But there is also some component from the absorption of solar radiation at the surface, so we can take advantage of this geothermal, shallow geothermal energy with heat pumps and using some technologies like borehole heat exchangers, for example. So as I said, this energy is stored in the rocks, soils, and also in the groundwater in the form of heat, and we can exploit this energy using different technologies. So next slide, please. So in this figure at the right, we have different technologies. You can see they are divided in two types. We call shallow geothermal and deep geothermal. Shallow geothermal energy, we need ground source heat pumps to extract. This could be borehole heat exchangers or closed loop, open holes where we can abstract water and reinject water. These are both valid for cooling and heating. And we could also use water stored in closed mines that have been flooded after abandonment, and we can use this water stored in these deep mines. In the deep geothermal technologies, we have hydrothermal systems. So these are deep aquifers. Usually we talk about deep below 500 meters, but this is like a convention. So it could be usually it's deeper, is around 1 kilometer, 2 kilometers depth to reach the temperatures we need for direct heating for buildings or for heating, for space heating. Another option of deep geothermal is the repurposing of oil gas. So these oil gas that are available at abandonment can be repurposed for heat exchangers. This is it's under development, so this is not a developed technologies for now. And the final type of technology is the use of the heat in granite. So we have some examples in the southwest, in Cornwall, United Downs, and in geothermal. So it's usage of these granites, usually fracture, that allow the flow of water. If we look at the figure at the left, we see the two different ranges of temperatures that could use. So we have the hot sedimentary aquifers that are useful for direct heating, temperatures between 60, 80, 100 degrees Celsius. As I said, depths around 1.5 kilometers, 2.5 kilometers, even deeper. And then the radiothermal granites, as in United Downs, we can reach temperatures up to 200 degrees, and these are we can use this for power generation. So next slide, please. So we have done a preliminary analysis with the information we have of the deep basins, so these hot sedimentary aquifers of the top 209 NHS hospitals, and based on heat demand. So from this analysis, we have come with 109 sites on top of potential geothermal aquifers. And we are talking here only of deep geothermal, because shallow geothermal, as I said, using heat pumps could be achievable in different hospitals. So in the figure at the right, you have 4 different colors. So 3 of these colors are these sedimentary basins, hot sedimentary aquifers. You can see in yellow, these are the Permo-Triassic basins. In blue, these are the Carboniferous limestone. And in green is the middle border group in the northeast, or the failed sandstone is also called. So these aquifers, we can extract water. We can use boreholes, abstract the water, that is hot water, and use this water for direct use for space heating. And then there is another resource that is in the granites. So there's radiogenic granites. You can see that in red colors in the figure. And there are only three sites on top of these granites in this preliminary analysis we have done. So the opportunities vary within these basins. So we have done more detailed analysis trying to understand the size of the resource and the depth to the resource. So next slide, please. So I'm going to present some of these more detailed analysis in these basins. I'm going to start for the Northeast. As I said, these are preliminary analysis, and we need to assess in more detail the resource. What we have done is to get the size of the basin, the depth of the basin, the thickness, and and use some analysis to estimate the resource or the heat in place. This is the maximum amount of heat that could be extracted. This is not the final amount you can extract, because it is not possible, but it's a first step to go into this assessment. So you can see in more detail the location of some of the hospitals. With this symbol, you can see the size in terms of heat demand. So we have done these prioritizations with the location. And you can see this heat in place values range between 1 in blue to 250 petajoules per kilometer square. When using the technique to abstract the water, usually we use doublets. A doublet is an abstraction well and a reinjection well. The footprint is around 1 to 2 kilometers square. And usually a conversion factor is between, when it's around 100 petajoules per kilometer square, is around 10 megawatts heat, something like that. But of course, it needs more assessment. And of course, these are preliminary results and a preliminary analysis. So this is a first step or a first stage in this analysis. So next slide, please. We have here more details. At the left, we have the Carboniferous limestone, the distribution of the Carboniferous limestone. You can see some main cities, Manchester, Liverpool. And you see that there is a blue color. This is the extent of the Carboniferous limestone. And then with the colors for the geothermal resource or the estimations of the heat in place is only for those depths below 500 meters depth, because we assume that the temperatures above this or in the shallower domains is not enough for direct heating. So we only have cells in the deeper parts of the basin. And at the right, we have two different basins, but we have, in this case, is for the Sherwood sandstone. So we have for Cheshire and we have for the east. And it's a Sherwood sandstone, so it has a different type of aquifer, but you can see as well that there are some areas of interest. And something that is important to understand, you can see, for example, in the figure at the right, you see Liverpool. So you have one reservoir on top of the other. So we can have, for example, the Sherwood sandstone and the Carboniferous limestone. So if we go deeper, we can reach another reservoir. So it's something that we have to take in mind when we assess the resources. It's not only the resource from one aquifer, but we can have different aquifers, one on top of the other. And in this analysis, we have only assessed the main aquifers and the main targets. So as I said, the next step, we'll have to do this in more detail. So next slide, please. And here we have a couple of maps for the south. We have the Wessex Basin. You see as well the distribution in yellow is the extent of the basin for the Sherwood sandstone as well. And with colors only the estimated heat in place depths below 500 meters. Here the estimated resource a bit smaller, but you have to think that we had in Southampton, we had the only operational deep geothermal well for over 30 years, producing at 1.8 megawatts thermal, and it was in use or in operation for almost 30 years and successfully. So is the resource is something that, yes, we have to assess in more detail, but the resource is there and it's been proved specifically for Southampton. So it's something that is there. And the same at the right, we have the stand in yellow of the Sherborne sandstone and the same estimates of the geothermal resource. So next slide, please. And finally, this is for the Carboniferous limestone and the Sherborne sandstone together. And you can see here, for example, for Bristol, Bath, that the resource is bigger for the Carboniferous limestone than in the previous map. So because the main resource is in the limestone is a bit deeper, but we know, and of course we know for the thermal springs that the resource is there. So we have estimated these quite high values of heat in place in these areas south of Bath, south of Bristol, that could be used for direct heat. And finally, there is some parts of the southwest Permian granites, but we didn't estimate the geothermal resource for the Permian granites because the estimation is different. So how we take the resource or how we take the heat out of the granites is slightly different. So we only have estimated for the sedimentary basis where we can pump the water from these aquifers, from these deep aquifers. So next slide, please. Previous one, yeah, I think. Yep. So we have ranked the hospitals in these basins using the heat demand. We have estimated the savings, the CO2 savings compared to use of gas, and we have used the maps to estimate the depths to reach 50 degrees Celsius temperature using the previous maps. So you can see that it's between, let's say, 1,500 meters and 2,500 meters. In this range, we can reach temperatures of about 50 degrees Celsius. If we go deeper, we can get 60, 80 degrees Celsius. But this is under this preliminary assessment. In the figure at the right, this is so the circles, red, orange, yellow, are the hospitals in potential zones with the size of the circle related with the heat demand. And you can see all the rest of the hospitals in the small red circle. So there are some that are outside these preferential deep geothermal areas. But as I said, this could be this could use shallow geothermal technologies for the decarbonization of the states. So next slide, please. So we have estimated that developing this geothermal project, we could save this range of emissions up to 12% of emissions from the NHS England state, including this or developing these geothermal projects for the 30 top ranking hospital sites, based, of course, on heat demand and on transferring into the geothermal solution. So next slide, please. And finally, we have developed this roadmap. This is part of this roadmap that has been published in the Deep Geothermal White Paper, recently published. I think it will be explained in more detail later. So it's just some of the main steps from the pre-feasibility until the final operation and future decommissioning of the geothermal well. But as it will be explained later, I'll move to the next slide. And yeah, finally saying that we have developed and published this Deep Geothermal Energy white paper that's been published by the Northeast Local Enterprise Partnership. And we are also publishing a long report where you can find more details that we use and or the data we use to develop some of these maps, and also more details into the different steps and to potential options. And this will be published soon, this long report that will be a complementary report for the Deep Geothermal Energy white paper. And as I said, these results I've shown are a preliminary assessment. We are working now in improving these estimations and having improved maps and improved reservoir estimation or resource estimations. And we are planning to work on this, and we can provide inputs or help in the future. So that's me. Thanks.
Thank you very much. Rick, if you can explain who you are and get on with it.
Thank you. Good morning, everyone, or rather good afternoon. Hello, yes, I'm Rick Evans. I work for a geothermal company here in the UK called GT Energy, working with Clive and the rest of the team to promote the technology to you and others. I'm sort of going to pick up from where Andreas left you. Well, I'm hoping enthused you with the opportunities that geothermal has beneath your feet for your particular hospitals. And you come away from this meeting and you think, yes, this is something I want to push forward with. The purpose of the next few minutes is really to talk you through the next steps. How do we take that concept of we might have an opportunity here and actually deliver you a working geothermal system? It doesn't happen overnight. We are fundamentally talking about something that is operating many tens of, if not hundreds, thousands of meters beneath the feet. And as a consequence of that, we are quite literally walking into the unknown. I put on the slide here a few of the challenges that brings with it. First and foremost, as you heard from Andreas actually a minute ago, is we have some concepts that the rock may be heat bearing. We have a view that heat may be extractable, but as a project deliverer, I then need to be able to ascertain that is the case in order that we can push forward with a viable project. If you look at other resource industries which are targeting the unknown, for instance, the oil and gas industry, which is my own background, we typically talk about exploration and appraisal, and that's a series of wells that have been delivered and drilled into one location. This hasn't happened in many of the places that you're looking at, for the simple fact that quite often you're in the middle of cities. So drilling, there isn't a history of drilling that's gone on. So our projects need to take that into consideration in order to be able to identify whether or not there is a resource going after that. We work in a country that has very robust regulation regarding planning and permitting of activities. So how do we go about applying for that, and how do we about going through and getting a consented operation on your behalf? So we'll talk a little bit about that. And certainly, first and foremost, is actually the challenge of then turning that heat, assuming that we can extract it, and then hooking that up to your facilities. Andreas talked about the potential heat ranges. At the low end, for a deep geothermal system, we may be talking about 50, 60 degrees. At the top end, we may be talking about more than 100. But obviously, there's a challenge with then integrating that with your legacy installations, some of which may be decades, if not 100 years old. So we need to be able to turn that heat into something that's usable for you. And then, quite fundamentally here, we need to develop a viable project or the concept of a viable project that not only is going to make money for the developer, but actually fundamentally is going to save you money and time. It's all well and good having an obligation to decarbonize, but what is the best approach for you? Is it deep geothermal? Is it shallow geothermal? Is it some other form of heat pumps, perhaps an air source heat pump or similar, or the mine water opportunities that you saw from Andreas's slide? So one of the things that we do as we work through a project is actually look at the economics and the commerciality of any opportunity to ensure that you're working and plumping for the best solution. This is a nascent industry, and the government in their wisdom have identified that, and there are grants and other funding routes available for this, but which is obviously a good thing. But naturally, as with many Treasury-derived grant funding schemes, these are time-bounded activities. You have a finite amount of months and years to extract that money, draw down on it, and turn it into a viable project. So one of the challenges with a complex initiative like this is actually maximising the use of the grant at the most valuable point within the project cycle. So again, one of the key areas of focus within the project team, certainly at the front end, is to ensure that we're doing that in an optimal way that gives you that commercial heat extraction at the back end. Just to sort of wrap all of those challenges back up into reality, the picture on the left-hand side there talks a little bit about what we're trying to achieve, and I want to pick up a couple of the themes that Andreas started to introduce. When we talk about the geothermal project, we are almost always talking about a doublet, 2 wells. There's a production well marked in red in that diagram on the left, and the re-injection well on the right-hand side. And there's a very simple reason for wanting to do that. When you start to remove the water, the pressure drops down and your ability to produce more water in the future is impacted. If we re-inject the water, we keep the pressure up in there and you ensure that you've got a long-lived system. There are plants operational today which were drilled over 100 years ago, just demonstrating that longevity really is deliverable. The critical challenge, though, when you're re-injecting those produced waters and therefore hopefully cool down because you've taken all that lovely heat out of them, you want to make sure that you're re-injecting away from your zone of production. And that's why with those wells we show that they are spaced apart from one another. Ideally, we'd be looking to make sure that they're 1 or 2 kilometers apart from each other. And that's where the different types of rock comes into play, because we need to make sure that the water will get back from your injection point back to production. And that ensures that the pressure is maintained, as I said, but you don't want it to do it too quickly, because if you do it too quickly, there's not a chance for the water to heat back up again. And as a consequence, you don't get that longevity that I said we're looking for. So these, again, are the sorts of challenges that we're looking to resolve as we go through the project development cycle. And Clive, if you could just move to the next slide, we'll talk about that in some more detail. So we typically think of it as a 5-step process, and each of the steps it exists in its own right, but looking to de-risk the progression of the project through the next stages. So typically we would look at them as proceeding sequentially, and also proceeding with a sort of an injection of capital at that stage, which is then going to ensure that any capital invested future on is done to the maximum benefit. So we go through the initial phase of assessment, and what you heard from Andreas is actually probably 50–60% of that assessment phase. What we're looking to do is ensure that there really is an opportunity there, and come up with some conceptual ideas as to what's the best way of extracting that heat. So we need an idea of the temperature. You saw that in Andreas's slides. We need an idea of the rough locations. We need to come away from that with a concept and an additional cost of roughly what that's going to look like. From that stage, we move through into feasibility. Now what we're trying to do is say, well, is this concept that we've come up with, is it deliverable? Is it going to, are we targeting an area of rock that we think we can extract that heat from? Are we coming up with a well design for our doublet system, remember, that means we're going to be crossing too many areas of challenging geology, which would make it unviable, both from a technical or indeed from a financial perspective. We speak with the regulators, both from the planning and the permitting side, to ensure that they've got no fundamental issues, that there are no areas of outstanding natural beauty above it, that there's no scientific areas of scientific interest that we might want to ignore. Perhaps we're looking at extracting water from zones that lie beneath potable aquifers, and so we need to consider how to isolate our geothermal waters, which generally aren't the most pleasant when it comes to mineral contents. We're talking sort of salt content between maybe 5 and 10 times that of seawater. How do we keep that isolated from the potable aquifers and to ensure that the water resource is available for all? So these are the sorts of things that we're discussing through that pre-application phase, and then finally, and to the point I made earlier on, making sure that we've looked at this from a fully commercial perspective and can move a project that that will work for you in the long term. Then we go through the consenting phase, and that's about putting together a viable project design that can then be signed off by the planners, by the EA, and ensuring that the project is safe and will work in harmony with everything around it. Once we've got a viable project, it's then a case of going out and tendering that. I saw a question pop up, and I will answer it afterwards. But to give you rough ideas, a well design is going to be a single well is going to be of the order of £5 to £10 million, for instance. So a doublet, you can imagine, is going to be approximately double that, plus the energy systems on surface. So it's a capital intensive process with very, very, very robust tendering that needs to go around that to ensure best value for money. We come to the end of this process, and we put together a commercial package, which then wraps up those construction costs, which the developer will take on board, and then puts that into a service contract that will enable the developer to be paid back over the lifetime of the energy services contract. And once that's all wrapped up, sanction the project, go forward for financial close, and we actually get to the exciting bit, where we start cutting into the ground, building a drill pad. So to give you rough ideas, a drilling location is somewhere of the order of 5,000 to 6,000 square meters. And the drilling rig may be on that pad for perhaps 6 to 9 months whilst the drilling operation takes place. Obviously, the length of time is determined by how deep you're going to go. Drill the wells, and we test those for their production lifetime. Typically, what we will be doing will be to ensure that the project will obviously last as long as the contract that's been set up around it, but typically we'd be looking for a life of 50 to maybe even 100 years, like those projects that are referred to elsewhere in the world. So this is a resource that's going to be in place for many years, not just for the hospital, but also the surrounding neighbourhood. Hook that up to the existing facilities through an isolating heat exchanger. As I alluded to earlier on, the mineral waters that we're extracting from a geothermal well aren't particularly good. So what we want to do is keep them above surface for the minimum amount of time. The heat is extracted through a heat exchanger, but the water is returned, and that heat is then made available to your heating systems and circuits around the hospital, in much the same way that your gas boiler provides heat from a central location, and there's water circulated through a heating loop from that. Right. So that's the general philosophy of the 5-stage program. If Clive can move on to the next slide, what I'll talk through is a little bit more detail around the individual steps. So that assessment stage that we were introduced to by Andreas earlier on, illuminated that by the picture there in the middle. What we will then do is take that away and develop a more robust geothermal concept on the basis of that. So we'll look at the regions around your hospital. We will understand sort of the legacy data that has been made available. I alluded to oil and gas drilling programs that may have happened in the past, but also there will have possibly been something called seismic information that has been captured around that location. Sometimes there has, sometimes there hasn't, but what we'll do is explore that. We'll look at all the well data from historical surveys, and from that we will come up with a more detailed geological model that will start to enable us to put together a package of work that we can then follow through the remaining 4 stages. The most important next step for us is to determine how much more information do we need to put together. Sometimes, because there is good data or that those appraisal wells have been done, then we don't need to do anything more. In some areas of the country, perhaps where they're in city centres, that those appraisal programs haven't happened in the past, and we need to put together a seismic acquisition program that will enable us to augment the information that is out there. So what I'm showing at the bottom of the page there really is a design actually that we're working on for a hospital right now in the south of England. And there we're putting together a seismic plan which will be carried out across the next 3 months in order to go away and assess their assess what the geology looks down to about 2,500 meters. Clive, if you could move on. So in the middle of the page, that's the exciting bit. That's where we go out and actually acquire that seismic data. Those are vibroseismic trucks, and they go away, and you can see those big pads sitting between the wheel, and they put those down on the surface, and they literally vibrate them. And from that, much like an ultrasound works, we can use that to pick up a picture of what's going on underneath our feet. And that all gets processed together until ultimately we come up with a picture that looks like the top right hand corner there, and that's a three-dimensional geological model of the subsurface. This is for a project in the West Midlands, Stoke-on-Trent, and what we're trying to visualize there is not just the well paths, which are faint lines on there, but actually the major faults that exist in the area. And that's very, very important for us to understand, not just from a drilling perspective, in that we want to keep away from the fault plains, but from an end point, from where the drills are targeting. We actually want to be reasonably close, because that gives us that energy transfer that we were talking about on the original slides. It's the water that exists in those cracks that ultimately is the mechanism by which we can extract the heat. So we need to be in a fractured zone. We need to be close to where those big faults are in order to be able to extract the heat. And then in the bottom right hand corner, we've got the commercial modelling aspect, which looks at your existing heat demand, and from it inserts that we can deliver the heat that you need, but does it in a way that's viable for the hospital. Next slide, please, Clive. At this stage, what we're then looking to do is prepare the permits, the consenting process that I talked about earlier on. So we're pulling together designs, both at the surface and also of the wells, that we can put in front of the consenting authorities and the regulators and convince them that we have a safe and viable project to proceed with. And ultimately, this is boiling up to a series of applications that can be then put in front of the regulator and put in front of the planning authority in order for them to do that. Next slide, please. This is the final stage then before we get into construction itself. And what we're looking to do then is take those conceptual and more detailed designs that have been approved, and we develop our final commercial packages from that. So there's three-dimensional designs of the facilities. There's the wells have got to be built up. We then put those out in the form of sorts of numbers that I talked about in terms of construction costs, but also the services that need to go alongside that in terms of assessment of the rigor of the drilling process, and making sure that, for instance, the cementing and the casing has been done to the standards that are required by the regulator. So that all comes together as a commercial package, which has a number associated with it, and that number is a unit price per heat. As I said earlier on, typically the developer will be absorbing all of the costs associated with this, and then is paid back through a long-term energy supply agreement. So what we're looking to do is convert all of those costs that come in from the package suppliers and turn that into a price of heat on a 1 year, lasting out for maybe 20 years of the project. And then moving on to the last slide, if we can, please, Clive. We then get into construction. So unfortunately, he's not with us today, but in the bottom right-hand corner there, we've got Kieran Mullen, who we participated on a visit to a working geothermal plant in a place called Pullach, which is just outside of Munich in southern Germany. And as you can see there, the wellhead, the device in red, that's all that remains of the well site once it's been fully built. So the picture in the middle shows you a drilling rig in situ. That height is about 50 to 55 meters of height, but that all gets decommissioned and moves off site once the wells have been drilled, and all you're left with is that small red wellhead that you can see in the picture. The other items that we're showing here are sort of other samples of sites that have been constructed in recent time in the UK, and the one in the top right hand corner, that's the outside of the block that the wellhead sits in Pullock. But the most important thing all the way working through this process is to ensure that longevity of the resource. So the designs and the construction are taken forward on the most rigorous of standards to ensure that these do continue to last 50+ years out into the future. So that's my last slide. I've seen a number of questions have popped up as I've been going through. So I'll thank you for those, and I'll look to answer those, and we'll issue them later on. Thank you very much. Clive, back to you.
Brilliant. Thank you very much. Dr. Mullen isn't here. He's written a paper. It's in the invite. The link's in the invite. You can look at his paper and read a number of things that he's gathered together in quite a friendly way for you to see. So I suggest you have a look at that if you want more information. There's a lot of questions about procurement and finance and all the rest of it, and you've heard that some companies are prepared to roll this up and do the whole installation for you and take it back in an energy price. There is something called NH Power, which you might have seen on invites. That is a notional grouping of NHS trusts working together to implement projects. So we issued 5 projects. We issued a procurement for 5 projects earlier in the year. You've seen one or two of the slides from one of them at that project. So we did a trial procurement of 5 projects earlier in the year. Some of the people participating in that are on the call. So there's a certain amount of experience we have for in the procurement. The idea is we'll do more, and we'll do them in tranches. So I've tried to show you a 4-year project. We can't do 100 and something geothermal in one batch. We need to do them in a period of time. So I've kind of shown you how it might work in terms of batches. Going forward from this, we will repeat the talk, and the idea is we will so that people who've missed this can still see it, and you can go back and view it and show it to your colleagues if you wish. At IHEM in Manchester, you're invited to attend a workshop there where we can go face to face. We'll attempt to work out how a project should be batched if you want to, and if you want to collaborate, how you can take part in that, and you can meet people like Rick face to face and have a session with them. They will also have a session in the Energy Theatre in the main hall, so you can do that. And we're planning a road show in November, December to take some of this stuff onto the road so we can explain it. But I can see there are a ton of good questions. There are questions I recognize from the procurement program, so we will attempt to answer those as best we can for you, so you have some of the answers. And as I said, will all come out as we go on through the process. So the talks, you should have all this information when the talk and when the repeat is. So repeating this on the 13th of September, be the same talkers talking live. You can ask questions again, but the video will go on the link, and then there are the workshops that you can see. By the end of the workshop at IHEM, we're hoping that you will be in a position to decide which net zero technology you should follow. And basically there's hydrogen, geothermal, or district heating, probably with one of the other 2 involved in it. And then for a number of trusts who haven't really got an option of any of those, then we are doing a sort of technology talks later in the session towards the end of the month to try and give some help to trusts who haven't got an immediate route to net zero. So we're hoping that by the end of IHEM, you'll know what's working for you and what the size of your trouble is. And by the end of the roadshow, you should actually have some ballpark costs for your scheme. So we were trying to work up bulk costing arrangements so that trusts can try and contrast the likely costs of these installations. That concludes the thing. We're just about on time. any of the speakers spot a question they'd dearly like to answer live, or in the minute or two we got left? It's not sounding like that. I saw there was a question about who's on the list that's already been through BGS. Well, NH Power has the list. We will publish. Your invites indicated whether you were on the list or not, because you were asked, you told you should be there if it was suitable for you. And if it wasn't, then we just said you may want to attend. So you've got a clue in your invite, and we'll publish on the collaboration website, and we'll publish the list of trusts, so you will get that. I saw questions about fracking. This isn't fracking. It does look a bit like fracking, but it isn't. This is drilling a hole operation rather than trying to disturb the rocks and release gases and inject all kinds of nasty things. This isn't anything like that. But you will have to engage with people. Carry on, Rick.
Let me pick up on that one, because it is obviously one of much interest. Definitively not fracking. We rely, as my slide showed, and Andreas mentioned as well, we rely very much on the natural cracks within the rock. We are targeting generally two sorts of rock type. One are sandstones, which have pore spaces which the water exists in, and the other types are carbonates, limestones. The best way to think about that is, if you've ever seen sort of limestone pavement up in the York Moors and so on, it's rock with lots and lots of cracks through it. So those cracks are holding water. Some of them are millimeter type cracks, and some of them are, tens of centimeters, if not meters in diameter, where you've got rocks and so on going through it. So we're targeting those sort of zones because they already have got the natural fractures in the rock. When you've got that sort of geology, you don't need to go about fracking.
Okay. I still do see a hand up, Xavier. We are about out of time, but go on, give it a shot.
It's just a really quick, it's just a really quick one, which I did pop in the chat, but I didn't see an answer, so sorry if there was one. How does this combine with the British Geological Survey's open loop ground source heat pump screening tool online? Is it comparable? Is it more in depth? Your assessment you've currently done?
We ran the schemes through the BGS database, so it's a fairly high level approach. And as you heard Rick explain, there's probably another layer of work that needs to be undertaken. So this job is all about risk, because nobody's going to spend 20 million quid in the hope there's something down there. So there's sort of a £50,000 initial stage, which BGS have helped with. BGS are prepared to do more, but we'll have to cross their palm with silver because it costs them money to do it. And then there is a longer stage, which depends upon whether you've got to do seismic work or not, which could be £1 million quid, could even be more. And each of these stages, we use a procurement called an innovation partnership that allows you and your chosen supplier to make a decision about your willingness to go to the next stage, or how you feel about the risks, who's going to pay for what, and what will happen if it all goes wrong. And then about 2 years in, we say, right, okay, we're about to be there. Are we all good for this? And then if you are, then the hole gets drilled and the work gets done. And it could be the contractor funds that and rolls that up. The NHS is looking at collaborative finance. I've put all 100 and something trusts to the UK Infrastructure Bank, and I've asked them for 2.2 billion. Now, they're probably busy coughing on their porridge still. But that's the kind of thing we got to get on with, is pursuing sources of funding and finance, because nobody's sitting there with an open pocket that we can pick. We've got to go through the grants route or various routes to do this thing. Okay, I'm kind of aware we've run over time. We'll answer your questions. We'll post them. We'll post the list of trusts, and hopefully we'll see you all at the workshop and see your colleagues at the next call. So I thank everybody for that. I'll leave the chat open for a second if somebody wants to keep typing answers, and then I'll save the recording and then we'll post it online. So thank you to the speakers. Thank you all for coming, and I hope it was useful to you.